Alright, hello, I am Mila, and today I am here to teach you a physics topic. Namely, I will be teaching you magnetic force on a current carrying wire. Now, this is section 8.3 in your textbooks, but I'll be elaborating on it a bit more. And of course, there's a bunch of information that is included on the rest of this webpage, so go take a look at that as well. If this is the first lesson that you're looking at in this textbook due to magnetism, I'm going to suggest that you maybe go to AJ's page because he did the section before mine, which was magnetic force on a moving charge. And that applies a little bit here. So maybe familiarize yourself with that first and then come back and watch this lesson. So to go right into it, I hope that by now we're familiar with the notion that an electric current is made up of a collection of moving charges. So stuff like electrons or anything with a charge. And as we know from a previous learning, so the previous section, a moving charge does have a magnetic field. It generates its own magnetic field, and it will experience a magnetic force due to an external magnetic field applied around it. So therefore, we can extrapolate that a current carrying a wire, which is just a bunch of moving charges, will also create its own magnetic field. And this is also Ørsted's experiment from grade 11. I hope you'll remember that. So let's say we have this wire here. It's just going to be moving up, and it has a current running through it. Ørsted's law and Ørsted's experiment tells us that if our thumb is going in the way of our direction, the magnetic field that the wire or the current will generate will be going in the way that our fingers curl. So there's going to be a circle around it. I hope you forgive my bad drawing. And the magnetic field will be going this way. In short, it will be going into the page and then out of the page over here. So that is the field generated by the current in the wire. So a bunch of moving charges make one big magnetic field. So what's going to happen if we put this wire that has its own magnetic field in an external magnetic field? So just like the moving charge in external magnetic field, there's going to be a magnetic force on it. After all, that is the name of this lesson. And so that magnetic force is going to be felt by the wire. So the wire is going to move in the way the force is felt, and we can find that out using a right-hand rule, but we're not there yet. First, I want to tell you that the external magnetic field that's going to be applied to this wire must be perpendicular or at least on an angle to this wire in order for the force to be felt. So what's good is stuff like this. So maybe a 45-degree angle, or for the best results, with most force, you're going to want a right angle. And this is because of the way that the fields interact. So the way that the generated field interacts with the external magnetic field, they have to be perpendicular. They absolutely cannot be parallel because then nothing's going to happen. This is a little complicated as to why. I was researching it. I couldn't really find out much, but I did find two websites that sort of explain a bit more, and I have included links below this video alongside videos to Ørsted's experiment if you want to look a bit more into all of this. However, I just need you to remember that a magnetic force will only be felt when the magnetic field is perpendicular or at an angle to the current in the wire. So onto our right-hand rule. You can also see this principle that it must be perpendicular in the right-hand rule. After all, in the one that we learned previously, our thumb was the moving charge, or the velocity, the way that the charge was moving. Our fingers, or your index finger, were the magnetic field. And then the way that your palm, or your last three fingers, were facing was the direction of the magnetic force. Now, if the same thing is applied here, nothing changes aside from the fact that your thumb is the way that the current in the wire is traveling, your finger or fingers are the way that your magnetic field is traveling, and your palm or three fingers are the way that the magnetic force is traveling. So we can look at this in a diagram. So let's say that we have a current going this way. So that's going to be our thumb. That's all we have. Next, we have a magnetic field coming out of this board. So our fingers are going to be going straight, or like this. So we have our thumb going this way, we have our fingers going front, and where is our palm facing, or your fingers facing? It's going straight down. So this wire is going to be repelled downward. It's going to have a hell of a fun time going down. Now, this is all well and good. We have a nice concept. We're using Oersted's law. But what can we actually do with it? That's the question that I always ask myself. Well, there is an equation that we can derive from this. And of course, it has to do with current. And we're going to start not only with the equation for current, which is I is equal to Q over delta time. So the time that takes one of the charges to move. But it also includes our equation from the previous chapter, which is magnetic force is equal to Q, so the charge, times the velocity, times magnetic field, times sine of theta, so the way that the magnetic field was facing on the charge. So what are we going to do with these? They don't really seem to interact that much. Well, let's take a look at a wire. Here's our hypothetical wire. And there is a current going through it, and it's going that way, let's say. A segment of this wire is going to have a specific length. We're going to call it L. And there are, of course, charges moving through this wire since there's a current, and that's what's defined as a current. So it's going to take these charges some time to move from here to here. And that's going to be delta T. And we're going to look at this equation that we have right here. And what can we find? Which one of these values do you think is going to incorporate length, or something like distance, and time? I hope you said velocity, because it definitely is velocity. So we can take these two values and relate them in this way, where velocity is equal to the length, also known as the distance, over time. And we're going to take this, so our velocity, and we're going to sub this into our force equation. So the force magnetic is equal to Q times L over delta T, which is the velocity, times the magnetic field times sine of theta, so of your angle. And there's not much we can do with it at this point either, yeah? So let's rework it a little bit. We're going to change it to force is equal to Q over T. So that looks a bit familiar. I hope it looks a bit familiar. And we're going to have multiplied by our L and multiplied by the magnetic field and sine. So now, let's finish it off. I mean, we can see that this is just equal to the current. So what we're going to do is we're going to substitute current as Q over T. And our final equation is I as current, L as length, times B as magnetic field times sine of theta, theta being your angle. And this is no longer magnetic force because we do want to differentiate it from magnetic force on a moving charge. It's going to be on wire. So the force on the wire, it is still a magnetic force, but it is the magnetic force on the wire. And that is the equation that you will be using in most of your calculations and in most of your explanations because it relates everything quite nicely, I hope. And as I hope you remember from previous sections and maybe some common sense, this will only give you the magnitude of the magnetic force. It does not give you the direction because most of these are scalar quantities, or at least the things that we will be using are scalar. So what do you think we're going to use to find our direction? It is the right-hand rule, as I hope you remember. It's the easiest way to find the direction for the magnetic force, unless you want to do some maybe really complicated trigonometry. I suggest you just take your hand and look at how things will work out. So for most questions, what we're going to do is we're going to find the magnitude, and then we're going to look at our hand, and we're going to figure out what the direction is, and that will be your answer. So to summarize what we learned that a current is a collection of moving charges. Well, that was recap, but we still learned it. And these moving charges will create a magnetic field going in a circular direction around this wire. Now, if this wire is placed in external magnetic field, it will feel a force, and you can find the direction of that force using a right-hand rule. And to find the magnitude of that force, we can use this equation right here. Now, this was quite short, I guess, in my terms, but it is quite useful and quite important, especially for everyday things in our lives, such as, well, I guess what's something that carries a current and has a wire that you use in your everyday life? I'll give you a minute. Not that you can answer me, but the answer is a loudspeaker. You know, your speakers in your bedroom or on your computer or in your phone, not exactly in your phone, but they all use wires to amplify the sound. And they use magnetic fields to make the waves even bigger. And that's a really important concept, and we want to be able to understand how these concepts work. There's a bit more on loudspeakers in the textbook, and there's also something about electromagnetic pumps, and I've gone quite in depth below this video on electromagnetic pumps and their use in dialysis for kidneys. And that's actually quite interesting, so I really do hope you read it because it's a quite cool application of the principle that through a current carrying wire or a current carrying liquid, for example, a magnetic force will be felt through a field. And I suggest you take a look at that. I've included a bunch of links and stuff, a bunch of my sources that I encourage you to take a look at because it's all very interesting and research really always expands our brains. And it's all below my video and we'll all find this on the page. And I hope that was a useful lesson. I'll give you a few minutes to copy this down. And I hope you do well in physics. Go forth and do your magnetism problems and learn everything you can.